Welcome, my dear students. Today, on the 6th week and the lecture 2, we are going to, go ahead with those technologies for conversion of those diverse waste, what we started in the last class. We talked about those particular, the solid waste, which is basically a diverse mixture of whether you talk about your household, whether you talk about the waste which is generated out of your trade, your business, your institutes, and definitely, we have a major part of this particular, waste is basically organic waste. And in that section, in the last class, we also try to bring out that, how to segregate these different components of these your wastes which is being generated. As I said, it's a mixture, it's a diverse mixture. And there are, number of technologies which are available, whether you talk about your pyrolysis, whether you talk about gasification, or whether you talk about, anaerobic digestion. So definitely we will be dealing with all and with a specific example and how those particular, technologies they can be useful so that to evolve that much of energy, as well as we can recover some of those useful products as well, apart from producing energy. So in this class we are just going to talk about mostly, as I said, that during this 6th week we are going to deal with multiple segments, waste to energy approaches from solid waste. And at the same time, we will be also talking about those plastic management, the plastic waste. And I also said that in the beginning that, we will be talking about multiple technologies, whether you talk about incineration, pyrolysis, gasification, whether those hydrothermal intervention, anaerobic digestion, fermentation and chemical processes. And we will like to see that, how these technologies, because starting from the initial, the conventional to the most sophisticated one, but there are definitely, once you have that sort of sophistication, there are, huge advantages as well as few disadvantages as well. So we will like to see one by one. So if it is incineration process for your waste to energy, definitely the concept is very simple, which basically uses this particular municipal solid waste as a fuel source for power generation. And this is similar to conventional fossil fuel based power plants. And what it does, it actually converts those particular waste into thermal energy, reducing reliance on coal, oil or natural gas. So definitely, if we look at the energy generation process during the process of incineration, so what it is being done, it is combustion of your waste, which basically generates heat, which is used to boil your water, and steam which produced drives a turbine generating your electricity. And environmental and waste reduction benefits, there are multiple benefits of this particular incineration if you look at it. So definitely it can reduces the landfill waste volume to the tune of 90%, because when we were discussing in the last class that if you look at the the approaches by different countries, in most of the countries including India also, they used to put it under landfill. So this incineration is going to reduce your landfill waste volume up to 90% and prevents the release of 1 ton of carbon dioxide per ton of waste burned. Because this generated carbon dioxide is going to contribute your climate change, if you look at the climate change issues, definitely it is going to contribute those climatic aberration, and which is going to contribute at a greater extent to your climate change. Converts 2000 pounds of waste into 300 to 600 pounds of ash, reducing waste by approximately 87%. So that is, that is a huge power, particularly with reference to converting that huge or bulk waste and to a, smaller amount of. And waste composition and efficiency, particularly this solid waste which contains high energy materials such as your paper, plastic, yard waste and wood based products. So, particularly if we look at the United States, about 85% of this solid waste can be combusted for electricity generation. I was also giving that particular example that how this solid waste is being converted for electricity, particularly whatever it is there, only 12% they have been capable or they have been able to convert it in the form of electricity. Mass burn technology, the most common, this is waste to energy system. This is also widely used in United States as well as in the other parts of the world, including Asia, including India as well. So, which involves direct combustion of unprocessed this solid waste in large incinerators equipped with boilers and turbines to generate your electricity. So, if you look at the processes which is going to be involved in that, but once you put those waste into your this waste bunker and which is going to go through that particular furnace, and then you have your primary and secondary air, you are going to put that particular air into it, so that you create that sort of combustion or you synergize that sort of combustion, and after that post combustion chamber you have a boiler and steam system which actually induces for production of that sort of electricity, because this is going to be governed by mostly your thermal mediated process, and following of which you can always yield this flue gas cleaning and then stack, and then the objectivity of converting that waste to energy is being achieved. So, starting from that particular waste resources or waste which is being generated, and ultimately to that particular, whether you talk about that flue gas or the electricity is being generated. And if we look at the status of this incineration process worldwide, as I was mentioning, that it varies significantly, and this variation is basically based on mostly your economic development, whether you have that sort of sophistication to utilize those particular bigger amount of waste, or that sort of that whether we have been able to scale that sort of technology. So, that is also very important. Environmental regulations and public acceptance. So, these are the most important factors which make those variations across different countries in the world, and approximately 11% of the waste globally is incinerated, with the higher rates mostly for your plastic waste. Mostly it is among that particular waste which is being put it into that bunker, mostly it is the plastic is always going to be at the higher. If we look at the composition of that waste, definitely plastic is always will be the higher amount. However, the disposal of toxic residue like fly ash remains largely unregulated in many regions of the world. The next part after incineration is your pyrolysis. In the week 5 classes, I mentioned little bit about this pyrolysis. So, if we look at this waste to energy concept and considering this particular transformation, the most interesting is the liquid fraction, which is made up of oily compounds that can be used to produce liquid biofuels. Because once you go ahead with this, you are going to produce either biogas or bio-oil or maybe biochar, right? Produce liquid biofuels that can replace conventional fuel such as your diesel and petrol. Additionally, the gaseous fraction, which I was mentioning, that biogas, it is a synthesis gas that can also be used to obtain energy, as in gasification. And the solid fraction, which I mentioned, char, consists of char, which is usually used in agriculture or adsorption process. And pyrolysis can be other of those technologies used in biorefinery as well. And if you look at these techniques, that this waste to energy, this conversion process, that basically or using those thermally mediated process. That means that thermally this waste is being decomposed to solid waste in the absence of your oxygen and converting it into your energy rich products. And these are the key energy products which is derived out of this the process of pyrolysis. You can see over here how this waste is being put into those drying beds and then grinding and then put it into your pyrolysis reactor, And then you have your char removal is being done, that biochar which I mentioned, right? And this is being brought out from the system, and then you have your bio oil, and then finally you have your biogas. And then gas recycling, if it is needed, that gas recycling is also done. So what we understand that through this particular process of pyrolysis, the key energy products which is being produced is either your liquid bio-oil, which can replace your conventional fossil fuel I mentioned already, whether it is petrol or diesel, syngas, a synthesis gas that can be used for electricity generation, this is very important, and biochar, a carbon rich solid used particularly in your soil enhancement and adsorption processes. And this can be also used as a soil conditioner as well. And these pyrolysis types based on your energy output, because whether you go ahead with this particular process of pyrolysis in a very faster way, so or in a very slower way, so that is going to be decided based on this particular the energy which is coming out of the whole process or this operation. So you may have a slow pyrolysis which maximizes your biochar for carbon sequestration and soil application. Fast pyrolysis optimized for your liquid and biofuel production. That means if you are going ahead with your high temperature, definitely you will be able to get this pyrolysis is going to yield that sort of oil. And then flash pyrolysis, this is focuses on syngas generation or direct energy recovery, and which is mostly used for that electricity generation. And these pyrolysis reactors, particularly in terms of when we talk about these waste to energy applications, so either it can be rotary, moving and fixed based reactors are there, because once we go through that particular picture where we have seen that how this waste is being put into those particular reactor. So they may be rotary, moving and fixed bed reactors used for specific waste to energy applications. And then you may have a fluidized bed reactors which actually ensures efficient heat transfer and higher energy conversions. And if you wanted to achieving higher temperature or that energy conversion, definitely you have to use your microwave and vacuum pyrolysis. These are your all advanced techniques for your improved biofuel yield. In the process of this particular pyrolysis, catalysts have a definitive role in enhancing this energy recovery. Whether you talk about those metal based and microporous catalysts, they improve those conversion efficiency and fuel quality. And they basically supports your hydrogen production, bio-oil refinement and enhanced biochar stability. So these catalysts, they have a multiple role, either in terms of your oil yield, enhancement of oil yield, or it is with reference to the stability of that particular biochar which is being produced. Okay. And also it is also supports your hydrogen production as well. So what is the future trend and how this pyrolysis technology is evolving? So development of large scale continuous pyrolysis systems for industrial waste management is there, it is coming up. Integration with co-pyrolysis, mixed feedstock for enhanced energy recovery, because I was mentioning about that mostly it was covered by your plastic waste. But if somebody is trying for some integration of those particular waste material, and definitely those mixed feedstock can be worked out for your energy recovery at a higher rate. Research on catalyst regeneration for sustainable energy conversion. This is also people are trying to evolving that sort of technology or trying to make some sort of innovation in that area as well. So whether you talk about large scale development, that means that the scale upliftment is always going to be a priority. Whether you talk about co-pyrolysis, this is again going to be very, very important, because once you talk about those mixed feedstock. And the last one which is very important, your catalyst regeneration, whenever you talk about those sustainability, sustainable energy conversion as well. So this pyrolysis, if we look at globally, is gaining traction in both, whether you talk about developed or underdeveloped world. So everywhere people are trying to make some sort of improvement or refinement with this, especially for plastic waste, as I was giving emphasis on this, as a versatile and environment friendly technology. That means this pyrolysis is gaining your importance. The next technology which I am going to emphasize is your gasification techniques. And this particular gasification technique, this is also a thermochemical waste to energy intervention, means waste to energy, this technological intervention, that process that basically converts those waste to your syngas or synthesis gas using a controlled oxygen and high temperature. This temperature requirement is very, very important, particularly whenever we talk about this gasification. And at the same time, that controlled air, this is also very important. Two things is very important with reference to your gasification. One is your temperature, another is your controlled air or absence of that oxygen. So what are the feedstock for particularly gasification we are going to use? We can use any sort of solid waste, whether it is that mixture or sewage sludge, agriculture residues and industrial byproducts, they can be used mostly. And you need a pre-treatment as well. If you have this sort of, mostly if it is agricultural residues, definitely it is going to contain much of moisture. So you need to make that sort of moisture reduction as well. At the same time, the size is going to enhance its efficiency for producing that syngas. So this size adjustment or that porous material, whether the porosity of that particular material as well as the size fractions, which are very, very important and may be required. So key energy products, like in pyrolysis we have seen that either we are going to produce biogas or bio oil or biochar, and here what is the main product? The main product is syngas, which is basically carbon monoxide and hydrogen used for heat, electricity and hydrogen production and biofuels. And the next is biochar. Biochar is also, like your pyrolysis, we are also producing biochar over here, a carbon rich product. I mentioned couple of times that this is going to be a wonderful product, particularly for if you look at your carbon sequestration and with a high energy content used in mostly your soil application, looking at those sustainability of your agriculture. And gasification technologies, particularly with reference to this waste to energy, there are, you may have a fixed bed gasifier, you may have a fluidized bed gasifier, or you may have an entrained flow or plasma gasification. And once we go ahead from fixed bed to your plasma gasification, always we are trying to, achieve more temperature so as to get or having more enhancement in the oil yield or in that, electricity yield. Mostly here, particularly in gasification, our main objectivity is we wanted to have more of syngas. So definitely, and each technology has its niche depending on the feedstock, desired output and operational constraints. So whatever I mentioned during this particular gasification process, once we are putting that particular carbon source feedstock, you are putting this waste and then you make a slurry with the water and then you put it into gasifier and then you create that temperature, and in absence of your, as I was mentioning, that it's a control oxygen which have to be there, and then you also make sure this particular removal of your either nitrogen oxides or sulfur oxide sort of material, that means acid gas removal is always done, and then you have to do that sort of carbon monoxide conversion, because it is a mixture of that. If you look at the syngas, basically this is nothing but your, as I said, that carbon monoxide and hydrogen, and ultimately once that carbon dioxide is being captured, and then ultimately we wanted to obtain this carbon monoxide and hydrogen, and which is basically you can see over here that from there this power or electricity is being generated. This is something which relates to this particular gasification techniques. I mentioned about those definitive technologies, whether it is fixed based, fluidized based and entrained flow or plasma gasification, and these are those the structure how it actually works, right? So particularly in fixed bed gasifier, the fuel basically moves slowly through that particular fixed bed, reacting with your gasifying agents, air, oxygen or steam. This is a simple design, high carbon conversion is possible and flexibility with feedstock. So even the mixture of those feedstock or mixture of those waste material can work out with this, and challenges, the tar formation can be significant, requiring additional cleanup. So we need to have that sort of sophistication for cleaning up those tar as well. And if it is fluidized bed gasifier, basically here fuel particles are suspended in a fluid like state using a gas flow and ensuring uniform temperature here, right here through is that particular feed here from here, and you can see that particular fixed bed, but here you are going to make that particular entry of your material through here. So what you are going to do, you are going to as I was mentioning, that ensuring a uniform temperature and efficient mixing you have to do that air, and here you are putting that particular steam, and high heat transfer rates, fuel flexibility, and better tar decomposition, which is very, very important. Once your material is going to put over here in this particular bed, so definitely it has a it's not going to be similar like your fixed bed gasifier, where you have an issues of your tar, or you have an issues which which you need to make those cleaning up mechanism. And in case of entrained flow gasifier, here fine coal particles are entrained in a high temperature, high pressure gas stream, leading to your rapid gasification. So from this to this, so definitely we are, as I was mentioning, the temperature is very important. Maybe initially from 600 to 800 to we will be reaching towards 100, 1800 or 1200 or 1400 degrees Celsius. So, and once we do that, that temperature increase, definitely it is going to make that sort of carbon conversion more easier. You have a tar-free syngas. So that means that impurities here will be always high, followed by these and followed by these, means this is going to be the minimum impurities you can always expect. And so whatever syngas you are going to get over here, so this is going to contain more pure. So that can be converted for those electricity generation, but you have challenges as well, that high energy requirement, as I was mentioning, that you have to achieve that high temperature, and maintenance due to extreme operating conditions, because once you go ahead with that sort of operating conditions, definitely you need to look into this particular context as well, because ultimately at the end of the day we always try to find out those sort of sustainable energy calculations. So if we wanted to go ahead with those sort of sustainable energy calculation, what is the input and output, definitely these issues will come. So these gasification technology adoption, again, as I was mentioning, for pyrolysis across varies widely, and influenced by factors like your energy policies of that particular country, feedstock availability, and technological advancement. Because what sort of bed are available for making those sort of gasification implication. So definitely that is going to be very, very important. And China is always taking a very important lead, particularly if you talk about those coal gasification. Germany and Sweden, particularly in terms whenever we look at to your European Union, so they are pioneers particularly for biomass gasification. Japan is known for its advanced waste to energy gasification plants, and in India also this gasification is gaining momentum, right, especially for biomass and this municipal solid waste, which we are giving emphasis in this particular class, right. And the last one which I am going to discuss in today's class is related to your hydrothermal process. And this hydrothermal process is a self-explanatory, which actually uses high temperature and pressure to convert these wet waste into a high energy fuels and value added chemicals, and making them a promising waste to energy technology you can see over here. So definitely you have your temperature mediation, at the same time your pressure is also being monitored and triggered, particularly for this process to happen. And you from those particular waste materials, so this is going to be biomass or organic waste, which is going to be over here, and through this hydrothermal carbonization you can always go ahead with this. You have a solid water separation unit, and from there you can always process your water, and through your anaerobic digestion always you can reach your methane, right. And from here, from this solid water separation unit, you can get those sort of hydrochar. because it is mostly, just in the previous case, whether it is in terms of pyrolysis and gasification, we have seen it is biochar. But here, as the name says everything, hydrothermal intervention, so definitely it is going to be a hydrochar instead of biochar. So this becomes with this solid biofuel, and it is going to be, we need to make that sort of combustion process effective. And once we do that, definitely we will be able to produce that in terms of your heat or electricity or generation of those syngases which are capable to generate this electricity. So from this process, so this is also in both way you are going to get your methane, as well as, because mostly the waste material are rich in organic resources, definitely you will be capable to produce your methane, as well as through this particular combustion you will be able to produce your syngas as well. So this, if we just now have a look at the types of these hydrothermal processes and energy products. So there are hydrothermal carbonization, which produces your hydrochar, which I mentioned, right? So which actually used as solid fuel, solid amendment, hydrothermal liquefaction, which basically within that temperature range 250 to 350 degrees Celsius, produces bio-crude oil, which refined into biofuels, and then hydrothermal gasification, which basically more than 374 degrees Celsius, and which produce syngas, which I was mentioning over there, that which is capable to produce that energy and hydrogen production and can be used for your electricity, right? So these waste feedstocks for your hydrothermal waste works efficiently with high moisture waste, reducing your drying cost. Basically, as I was mentioning, particularly for your pyrolysis and gasification, where drying is a must. But here, if you have that sort of waste which is containing much of your moisture, definitely it's not any issue over there. That means you can always reduce your drying cost. And suitable for food waste, plastics, paper, agriculture, forestry and textile waste. And current research, if you look at that, what is the development is happening in this particular hydrothermal waste to energy intervention. So most laboratory scale studies with batch reactors and catalysts. So it is an inception stage, right? Industrial scale continuous reactors process for your biomass and waste efficiently. Yes, there are few motivations are also there. And future trends in this hydrothermal waste to energy, development of large scale hydrothermal reactors for continuous operation, if it could be done. Definitely it is a wonderful solution, because you can use those particular waste with much of moisture and also with those dried waste as well. Integration with other waste to energy technology process like your anaerobic digestion and combustion, and exploring synergistic effects of mixed waste feedstock to enhance efficiency. I was giving emphasis on this particular issue, that mixed waste feedstock. So once we are capable to use this or scale up this technology, definitely we will be able to use this hydrothermal this sort of technology for this conversion of this waste into your definitely your energy. And this hydrothermal process or waste conversions are, as I said, it is, although at its inception stage, but it's also gaining popularity as sustainable solution for managing diverse waste system, particularly in Japan, European Union and Australia, they are taking most of your lead. So now in today's class, so what we understand that we try to analyze the context of different technologies which are available, and particularly we mentioned about pyrolysis, we mentioned about gasification, we mentioned about incineration, which is basically in a primitive stage, but yes, definitely there are multiple sort of development that has made that incineration techniques more refined. And at the last we also discussed with those hydrothermal intervention, and this is an wonderful technology. But yes, it's a long distance to travel, because still it has to be scaled up. This industry or this technology has to scaled up, and definitely in the next few classes we will be talking about the other technological options. Thank you very much.